Welcome to qnawire.
What we're going to do is take the derivation for what is going to be the electric field of a dipole at a certain point P that is right on the middle over here. So the first thing that we're going to identify is the fact that the x component is going to be canceled out because E net on x is going to be equal to E positive on x plus E negative on x. Both are going to have the same magnitude but opposite directions, so this is going to give us 0 direct. Thus, the only component that we really care about is going to be the component on the y-axis. On the y-axis, what we're going to get is that in order to know the distance, I'm going to identify a different angle, theta, that is going to be 1/2 of phi. So that 2 times theta would give us the angle phi that is given over here on the picture. For both of the charges that we're going to have, the distance in between the charge and P, Q and P, is going to be equal to the square. Actually, let's say directly the distance squared because that's the quantity that we care about, is going to be equal to r squared plus s squared over 4. This comes from s over 2 squared. Okay. Thus, the electric field on the y direction is going to be the electric field from the positive charge on y plus the electric field on the negative charge on y. Notice that both of the vectors are going to be on the negative x-axis. Both of them are going to have the component going down with respect to the origin, that is this point. So this is going to become, for E positive y, we're going to get minus Coulomb's constant times the charge divided by distance squared, which is r squared plus s squared over 4. And this is going to be multiplied by the sine of theta. On the other hand, we're going to have the same quantity, minus kq divided by r squared plus s squared divided by 4, and also multiplied by the sine of theta to get the y component. In this case, the minus comes from different parts. On the first scenario, the minus comes from the fact of the, due to the repulsion that we're going to get, and on the second case, it comes from the attraction interaction that goes in this direction. Okay? So now with this, we know that the electric field on y would be equal to minus 2 times kq divided by r squared plus s squared divided by 4 times the sine of theta. Now with this, what we can get is, under the approximation that are given to us, meaning r is much larger than s and the angle theta, it would be close to 0, but essentially what is going to happen over here is that the sine of theta would be equal to s over 2 divided by r, divided by the distance. So this is s over 2 divided by the square root of r squared plus s squared over 4, which under our approximation becomes s over 2 divided by r. Now, since r is going to be much larger than s, that means that r squared plus s squared over 4 is going to be approximately equal to r squared directly. Thus, the value for E on the y-axis is going to become minus 2 times kq divided by r squared, and instead of sine of theta, I'm going to employ s divided by 2 divided by r. The 2 and the 2 cancel out. This gives us minus kqs divided by r cubed, and q times s is nothing but the dipole, minus k times p divided by r cubed. And in this case, remember that the value for Coulomb's constant is going to be 1 over 4 pi epsilon 0. So let me emphasize that this is the dipole moment vector. So this is going to be equal 1 times 1 over 4 pi epsilon 0 times electric dipole divided by r cubed. And with that, we're done with the derivation.